Imagine walking into a bank, right? You pull out your latest account statement and you take a red pen to it.
Okay, I like where this is going.
You casually cross out your current balance, write in $1 million, and just hand it back to the teller.
And they just accept it.
Exactly. The teller looks at the scribble, nods, and says, "Have a great day, millionaire."
Right, which in the physical world is completely absurd.
Totally absurd. But in the digital world, that kind of blind acceptance happens like every single day. Welcome to the Deep Dive.
Glad to be here.
So today, our mission is to unpack this really fascinating official EC Council curriculum module on hacking web applications.
Yeah, it's a dense one.
It really is. We're looking at the actual architecture of the modern web. We're going to get into this concept called the 7-layer vulnerability stack. And of course, the famous OWASP top 10 application security risks.
Which is pretty much the gold standard for this stuff.
Right. We are going to decode exactly how attackers manipulate the digital systems you rely on to do everything, from checking your email to managing your retirement funds.
Yeah, and it really requires a fundamental shift in how you view the tools you use every day.
How so?
Well, we tend to view web applications as these polished, impenetrable surfaces, right? But understanding how they're broken is genuinely the only way to understand how they work. I mean, when you see the flaws, you see the actual blueprint of the internet.
So let's start with that blueprint then. Because to understand how attackers break in, we really have to know what they're actually poking at.
Exact.
I know you listening are probably familiar with the basics of clients and servers, but the source material breaks modern web applications down into a very specific 3-layer architecture.
Yeah, and it's a good way to visualize it.
Right, so you have the presentation layer, which is just the browser rendering the HTML and JavaScript on your actual device.
Yeah, the front end.
Yeah. Then behind that, you've got the business logic layer running on the web server. So that's the Apache or ISO server, handling the functional code written in, say, .NET or Java.
The brains of the operation.
Exactly. And finally, the database layer in the back, holding the actual treasure, right? Yeah. The MS SQL or MySQL servers, storing the user IDs, commercial records, passwords, all that.
And the critical thing to understand about those 3 layers is how they communicate. Like, they don't just exist in a vacuum.
Right, they have to talk.
Exactly. The sources emphasize the role of web services here. You'll see terms like SOAP and RESTful services.
It's a connective tissue, basically.
Yeah, essentially. They allow applications developed on completely different platforms to talk to each other across the internet. And they're usually passing data back and forth using XML or JSON over standard HTTP.
Got it.
And SOP is this highly rigid contract-based protocol, whereas RESTful is a more flexible approach based on accessing resource states.
But the real issue is just the amount of data moving around, right?
Oh, absolutely. The overarching vulnerability is the sheer volume of data constantly moving between these disparate layers and services. Every single handoff is a potential intercept point.
Which perfectly sets us up for the vulnerability stack.
Right.
Because the EC Council curriculum breaks the total attack surface down into 7 distinct layers.
Yep, working from the bottom up.
Exactly. Layer 1 is security, firewalls and intrusion detection. Layer 2 is the physical network routers. Layer 3 is the operating system.
Layer 4 is the database.
Right. Layer 5 is the web server software itself. Layer 6 represents all the third-party components and plugins. And finally, Layer 7, sitting at the very top, is the custom web application.
The actual code the company wrote.
Yeah. And if you look closely at that stack, you start to see this massive structural disadvantage for the defenders.
Oh, it's huge, because an attacker only needs to find a critical flaw in one of those 7 layers to gain a foothold.
Right. I was trying to visualize that earlier. Like, if an application is a fortress, it sounds like developers have to guard 7 different doors simultaneously.
All at the same time.
Yeah. From the outermost network perimeter all the way up to the custom business logic they just pushed to production that morning. Are we essentially asking development teams to do the impossible? I mean, guarding every single door flawlessly while the attacker just walks around testing knobs until one turns?
Honestly.
Yes.
So how do they manage that?
Well, often they don't.
Really?
Yeah, because each of those 7 layers requires highly specialized, entirely different expertise.
Oh, I see what you mean.
Right, like a brilliant software developer writing Layer 7 business logic in C# might be an absolute visionary at building a seamless user experience.
But they might not know networking.
Exactly. They might have absolutely zero knowledge of how to securely configure the Layer 3 Linux operating system that their application is eventually hosted on.
Right.
They might not know the first thing about hardening the Layer 5 Apache server to prevent buffer overflows.
So it's just this siloed expertise. Yeah, and that creates massive blind spots. Attackers scan all 7 layers, specifically looking for the one IT administrator or developer who was, operating outside their depth and just made a single configuration mistake.
Wow. So let's focus on the top of that stack then. Layer 7, the custom web apps.
The Wild West.
Seriously. Since this layer is entirely unique to every single company, its custom code, the text suggests it is frequently the most vulnerable.
Without a doubt.
Which brings us directly to how attackers manipulate that specific business logic. And that's mapped out in the OWASP Top 10.
The Open Web Application Security Project?
Right, the gold standard list for critical risks.
Yeah.
And number 1 on their most recent list is broken access control.
Yeah, and broken access control is essentially the digital version of someone walking into a corporate office wearing a really convincing suit.
And just acting like they belong there.
Exactly, just walking around until they're literally sitting at the CEO's desk. It allows attackers to act as regular users or administrators, completely bypassing authentication checks.
And the mechanism for how they pull that off is just fascinating. Our sources detail this thing called parameter and form tampering.
Yeah, this is where it gets crazy.
Right. So web apps frequently store critical transaction information in hidden HTML fields. The text gives an example of a hidden input field for a product price.
The $99 example.
Yeah. In the code, it literally reads like input type equals hidden, name equals price, value equals 99.90. Or sometimes this data is passed right in the URL itself.
Right, in plain sight.
Like you might see a web address ending in debit equals 2500. And attackers use these proxy tools, like one mentioned called Web Scarab, to intercept the communication as it leaves the browser but before it hits the server.
And the sheer simplicity of the exploit is what catches most people off guard.
It really is. Like, you're telling me an attacker can just run a proxy, intercept the web page data, and manually change that hidden price text from $99.09 to a single dollar.
Yep.
Or change the URL from a debit of $2,500 to $1,500, and the server just accepts it.
It does.
That's my bank teller analogy from the start. I mean, it's like putting a sticky note with a $1 barcode over a giant flat-screen TV at a retail store and just expecting the cashier not to notice.
And your retail analogy hits the mechanism perfectly provided. You imagine that the cashier is completely blindfolded.
Oh, wow.
Right, because the blindfolded cashier only knows how to scan the barcode handed to them by the customer. The web server doesn't have the contextual awareness a human cashier does.
That's terrifying.
It is. And the reason the server accepts the altered price comes down to OWASP risk number 4, which is insecure design.
But why design it so the server is blindfolded in the first place?
Well, it happens when development teams prioritize speed and functionality over business risk profiling. They just inherently trust the client-side data.
The browser.
Exactly. The logic is flawed, but super common. The developer assumes that because the server originally sent the price of $99.90 to the browser will just faithfully return that exact same price.
Without tampering.
Right, so they fail to build a mechanism to validate that data on the server side before executing the transaction.
They don't double check.
No, they don't force the application to check the backend database again and ask, wait, is this television actually retail priced at $1? They just process the tampered parameter because it arrived in the expected format.
That level of misplaced trust is just staggering.
It's everywhere, too.
But let's look at what happens when the attacker's goal isn't just to change a price tag. I mean, what if they don't want to buy the TV for $1? What if they want to break into the back office and steal the entire customer ledger?
Now we're getting into the really dangerous stuff.
Right. This moves us into OSP number 3, which is injection. The text highlights SQL injection, LDAP injection, and cross-site scripting.
Yeah, and injection attacks exploit this fundamental confusion within the application's interpreter.
Fusion.
Yeah, the problem is that the database engine can't inherently tell the difference between data and instructions.
How does that confusion actually play out in practice?
Okay, so think about the standard login box, or like a search field. You are supposed to type your name.
Right.
But if you type a database command instead, something like drop table or select all, and the application doesn't sanitize that input.
It just passes it through.
Exactly. It passes your raw text straight to the database. The database doesn't see a weirdly formatted name. It sees a direct authoritative order from its boss, the web server.
Oh, man.
So it executes the command. And suddenly, the attacker is downloading the entire table of encrypted user passwords.
Just from typing into a search box.
Yep. And LDIP injection works on the exact same principle, but it targets the lightweight directory access protocol.
Which is what?
That's the directory of who is who in the company network. So you aren't just messing with a database, you're messing with the company's internal phone book and permission structures.
And then cross-site scripting, or XSS, that kind of shifts the target entirely, right?
It does.
Because instead of tricking the back-end server, the attacker injects malicious JavaScript into the web application so that other users' browsers execute it.
Right. They turn the trusted application into a distribution mechanism.
To attack the app's own users. But I think the injection flaw that really stood out to me in the sources is oversight number 10.
Server-side request forgery, SSRF.
SSRF, yeah.
SSRF is this uniquely dangerous modern problem because it leverages the architecture we discussed earlier against itself.
How so?
Well, web servers usually sit in a demilitarized zone, right, a DMZ. They have to be allowed to talk to the public internet to serve customers, obviously, but they also have to be allowed to talk to the deeply hidden, heavily firewalled internal backend servers to fetch data.
So the attacker leverages that privileged position.
Exactly.
Because the text gives some wild examples of SSRF payloads. An attacker manipulates a URL parameter, but instead of injecting SQL code or changing a price, they inject a local file path.
Right, they point inward.
Yeah. They force the web server to read its own highly sensitive internal operating system files using a command like, file : ///, /passroot.
Yep.
Or they force the web server to scan internal network ports using a URL like localhost : 22.
They are literally turning the company's public-facing web server into an internal spy.
It's basically a digital vampire.
I like that analogy.
Right, because it cannot enter the internal firewalled network unless the web server explicitly invites it in. But once that malicious request is processed by the web server, it has free rein to look around inside.
Exactly.
But I'm trying to figure out, how does a company's robust external firewall even help if the malicious request is technically originating from inside the house?
The harsh reality is that the external firewall doesn't help at all.
Not at all.
No, the firewall is completely blind to this attack because it is looking outward at the perimeter, right? It's filtering external noise. And back-end internal servers inherently trust requests coming from the web server because they reside on the same trusted internal network.
Wow.
So this is the ultimate failure of relying solely on perimeter defense. It proves why defense in depth is absolutely mandatory. I mean, firewalls cannot stop an attack if the application logic itself is successfully weaponized by the user's input.
So the application has to be smarter.
Yeah, the application has to be engineered to refuse arbitrary internal requests, even if the request format is technically valid.
Okay, so attackers can weaponize the application to spy on the internal network. But sometimes they don't even need to craft complex injection payloads, do they?
Sometimes they just get lucky.
Right. Sometimes the developers accidentally just leave the blueprints to the entire infrastructure lying around in plain sight. Which brings us to OWASP number 5, security misconfiguration.
A very classic, very pervasive issue. We see this with insecure default settings all the time. Or like storage buckets in the cloud left wide open to the public without any authentication.
Right. But the most revealing misconfiguration usually comes down to improper error handling.
Oh yeah, that's a big one.
The text gives a brilliant example of this. An application throws a generic error, but the developer accidentally left debug mode on.
A classic mistake.
Yeah, so instead of just saying, oops, something went wrong, the screen actually displays the failed SQL query, the exact line of code where it failed, like line 435, and the internal directory path on the server.
It's terrible.
It literally hands the attacker a roadmap of the database structure. And the sources also detail directory traversal here.
Yeah, the ... attack.
Exactly. This is where an attacker manipulates URL variables using those ... sequences.
Yeah.
They type ... etc. / password to step backwards right out of the public web publishing directory.
To access restricted system files.
Yeah.
They're essentially walking out the back door of the approved web folder and just freely browsing the host operating system's root files.
So I have a logistical question about this. Logically, developers need highly detailed error logs to fix bugs. Right?
Absolutely. They can't work blind.
Right. If an application crashes at 2 a.m., the engineering team needs to know it happened on line 435 with that specific SQL query.
Yep.
So how do they balance getting the diagnostic telemetry they need to keep the site running without handing an attacker a topographical map of their infrastructure.
So you are pointing directly to the mitigation strategy outlined in OWASP number 9, which covers security logging and monitoring failures.
Okay.
The industry standard solution is a concept called output neutralization.
Output neutralization, like decoupling the data.
Decoupling what the system records internally from what the user experiences externally.
Got it.
Yeah, good security architecture dictates that when a fatal error occurs, the application logs all that rich, highly detailed diagnostic data line 435, the SQL syntax, the database version to a secure, internally monitored logging server.
That only the devs can see.
Exactly. Only the engineering team can access it. But the application logic should only ever display a generic, opaque message to the end user's browser.
So something completely sterile.
Yeah, something like an unexpected error occurred. Reference ID 892.
Oh, I see.
Right. So the attacker gets zero actionable intelligence, but the developer gets the exact thread they need to pull to fix the bug.
Hide the blueprints, keeps the data. That makes perfect sense.
It does.
But hiding the blueprints doesn't really matter if the locks on the doors are cheap or if someone can just steal your key.
True.
Let's talk about OWASP number 2. Cryptographic failures. Our EC Council source provides this really fascinating side-by-side code comparison of vulnerable code versus secure code.
Yeah, that example is very telling.
It is. The vulnerable code takes a user's sensitive data and simply runs it through a basic base64 encoding.
Which, just to be clear, calling base64 encoding cryptography is a very dangerous stretch.
Right. Looking at the example, using base64 instead of actual encryption is basically like writing your password in Pig Latin.
Exactly.
Sure, it looks scrambled to a casual observer glancing at the screen, but anyone who knows the rule can decode it instantly in reverse. There is no key.
Not at all.
So why are developers still making this fundamental mistake with sensitive data?
Well, because implementing true cryptography is difficult, and it introduces significant computational overhead to the server.
It slows things down.
Yes. If you look at the secure code example in the source material, it doesn't just scramble the letters with a known rule. It uses proper encryption standards like AES.
Okay.
And more importantly, it generates a secure random initialization vector, or 5e.
What does that do?
It ensures that even if you encrypt the exact same password twice, the output looks completely different each time.
Oh, nice.
Yeah, it defeats pattern recognition. Plus, it uses complex key derivation functions like PBKDF2 with HMAC HHA256.
That sounds like a really heavy process.
It is, and it's entirely by design. A key derivation function forces the system to run thousands of mathematical loops. It makes it computationally exhausting and incredibly slow for a hacker to attempt a brute force attack to guess the key. But that same mathematical exhaustion slows down the application slightly. So developers sometimes take shortcuts to improve server response times, or simply out of a lack of cryptographic knowledge, which results in weakly protected data being transmitted.
And even if the back-end cryptography is military grade, the application can still completely fail the user via OWASP number 7, which is identification and authentication failures.
Oh, definitely.
The text talks about session IDs being improperly exposed directly in the URL string, and this allows for an attack called session fixation.
Yeah, session fixation is a brilliant manipulation of state.
How does it work?
Imagine walking into a hotel, right? You take a room key card from the front desk, but instead of using it yourself, you hand it to the next legitimate guest who walks in.
Okay.
Once they check in at the desk and put their credit card on file for that specific room, you pull out your duplicate key and just raid the minibar.
Wow.
Right. If your unique session ID is just sitting visibly in the web address, an attacker can generate a link, trick you into logging in using their provided session ID, and then they have full access to your authenticated account.
Because you logged into their key.
Exactly.
The sources also mention timeout exploitation. Like, if a bank session timeout is set to 2 hours and you check your balance on a public library computer, close the browser without hitting log out, and just walk away.
Someone else can sit down.
Right. An attacker sits down an hour later, reopens the browser history, and your session is still perfectly valid. They have your keys.
It is the ultimate collision between user convenience and security. Users hate logging in every 5 minutes, so businesses demand long session timeout.
And attackers exploit that.
Attackers rely on that exact business decision.
So up to this point, we've focused heavily on the custom code the developers write themselves, right?
Yeah.
Like their business logic, their error handling, their crypto choices.
The in-house stuff.
Yeah. But the reality is Nobody builds a modern web application from scratch anymore. They are mostly assembled from pre-existing code. Third-party libraries, open-source frameworks, and plugins written by entirely different people.
Yeah, modern software development is essentially modular assembly. You pull in a UI framework here, a database connector there. It saves thousands of hours of development time.
And this introduces a massive blind spot, the Trojan horse in the codebase.
OSP number 6.
Vulnerable and outdated components. The text notes that attackers don't even need to find a new flaw. They just scan web applications to identify which specific versions of third-party libraries are running, and then they check public databases.
Like the exploit database.
Oh, the zero-day initiative.
Yeah.
They're just looking for known, documented vulnerabilities in older, off-the-shelf components.
And the danger is amplified because these third-party components almost always run with the exact same system privileges as the main application.
Oh, really?
Yeah. A flaw in a tiny, obscure image resizing plugin can allow an attacker to compromise the entire host server.
Wait, I'm confused about the solution to this.
Yeah.
Because my computer yells at me constantly to update my software to stay secure.
Right. Patch everything.
Yeah. If developers know that older libraries get exploited, shouldn't the golden rule just be to turn on auto updates for every single component? Doesn't that instantly solve OWASP number 6?
That is the logical assumption, yeah. But it introduces one of the most fascinating contradictions in modern software development.
Which is?
Blindly accepting automatic updates actually causes a completely different, often more severe vulnerability. OWASP number 8. Software and data integrity failures.
Wait, how does patching a system cause a failure?
Through supply chain attacks via CI/CD pipelines.
Okay, unpack that.
So, modern development teams use continuous integration and continuous deployment pipelines to push code automatically, right?
Right.
If an organization configures their systems to blindly accept auto updates from a third-party repository without cryptographically verifying the digital signatures of that incoming code, they bypass all their own security checks.
Oh, I see where this is going.
Yeah. An attacker doesn't need to hack the target company directly. They hack the much smaller, less secure third-party vendor providing the update. They poison the library.
And then the update goes out.
Then the target company's own automated systems obediently download the attacker's malware and install it directly into their secure production environment, believing it to be a legitimate patch.
They literally open the fortress gates and drag the Trojan horse inside themselves automatically.
Exactly. You must update to stay secure against known flaws, but you cannot trust the updates implicitly. It requires rigorous, constant verification of every single dependency.
Wow. So bringing this all together, web applications offer us immense frictionless convenience. We run our entire lives, our finances, our medical records through them.
Everything.
But they rest on a massive, highly complex 7-layer stack of technologies. From manipulating hidden form parameters like blindfolding a cashier, to exploiting unpatched third-party libraries, to forcing a web server to spy on its own internal network through SSRF. The OWASP Top 10 reveals a recurring foundational theme here. The greatest vulnerability in any digital system is misplaced trust. Trusting client data, trusting internal network traffic, trusting automatic updates.
It's so true. Every single exploit mechanism we decoded today relies entirely on a system making a naive assumption about the data it was handed.
Exactly. So, to you listening, the next time you click buy on a retail website or log into a portal, think about the unseen layers of security that are working or failing to keep your session IDs, your passwords, and your data safe from traversal attacks and parameter tampering.
Yeah, think about the stack.
In that architecture diagram we discussed, you are the user, and your data is the ultimate prize they are after.
And maintaining that security requires a staggering amount of vigilance from the engineering teams.
It really does. Which leaves me with a final thought for everyone to chew on.
Let's hear it.
Given that modern web applications rely on thousands of nested third-party dependencies, running on operating systems configured by completely different teams, utilizing components that are constantly aging into obsolescence,
It's a lot.
is creating a truly secure web application actually an impossible goal? Are global organizations merely engaged in a continuous, endless game of patching holes just to maintain a baseline of acceptable vulnerability? It's something to ponder the next time your browser asks you to casually accept a cookie.
That is a very unsettling reality to consider.
We treat them like magic portals, but sometimes the magic is just an illusion.